Hey guys, it's Thursday. It's windy outside right now, so if you hear things battering against the side of the house, I apologize. That's just the wind. We're up in the attic. A few reminders. That okay. I guess these aren't reminders. Okay. A few notes. We're going to have a quiz next Friday. It's going to be over the homework from section 4.4, 4.2, and 5.4. You're like, Dr. Warren, why don't you have the 4.2 before the 4.4? Well, this is the way we did it. That's the order that we did those in, okay? Also, for tonight's homework, I want you reading section 5.5, and doing the homework in 5.4, part 2, which is 27, 31, 33, 35, 39, 43, 57, 59, and 69. Okay, let me remind you a little bit about what we did last time. We had a terribly long infinite series that represented e to the x, okay? And what we showed, it took some work. We used power rule. We used something with factorial, which we haven't talked about probably since you were in high school. We showed that the derivative of e to the x was e to the x. We also looked at e to the f of x, and this is probably the more important flashcard. Okay, that the derivative of e raised to anything, we argued, was e raised to that thing times the derivative of that thing. Okay, so it's e to the f of x is just e to the f of x times f prime of x. So even though these are complicated functions, their derivatives are really simple. For this one, you don't even think, you just write it down. For this one, you got to think a little bit. You write it down, and you take the derivative of the exponent. Let me give you an example. Okay, suppose I've got that f of x is equal to like e to the x squared plus 7x plus 4. Okay, and I want to use this second flashcard. Well, I guess I should call this g of x, so we don't get this confused. Well, you can see this is definitely not just x. This has got more stuff here. Okay, this part right here is my f of x. That's that part. Okay, so now when I take the derivative of this function, if this was asked of me, it would be e to the f of x. So I'm not even thinking. I'm thinking maybe I'll have something for dinner tonight. I haven't even thought. All I've done is take this thing and write it down again, then times the derivative of that. Now we're not done because we still need to take this derivative, but this would be e to the x squared plus 7x plus 4, then times the derivative of this, which hopefully everybody now could do, is 2x plus 7. Okay, so even though these are complicated functions, okay, they're incredibly useful, but their derivatives are not that bad. Okay. So now what I want you to do is just stand up because we're going to end up showing a result that that's going to be important, but I'm going to need you guys to have fresh minds when you do this. Okay, stand up, maybe stretch, go get yourself a drink of water, because we're gonna prove a result that's going to be important in developing properties of the exponential function. Okay. Well, hopefully you did that and you're coming back. So this is the result that I want to show you guys. Suppose that I've got a function whose derivative is equal to some constant times itself. I have a function whose derivative is equal to some constant times itself. And I've got some other function whose derivative is also equal to some constant times itself. Okay? And suppose I know one other thing, and that's that f of 0 is always equal to g of 0. Also, that f of 0 is equal to g of 0. So I've got this piece of information, this piece of information, and this piece of information. I have a function whose derivative is equal to some constant times itself, and I have some other function whose derivative is equal to some constant times itself. Now what I want to do is I want to look at the derivative of f over g. That's what I want to do. I'm going to look at the derivative of f over g. Now using your quotient rule, this is the derivative of f times g minus f times the derivative of g. You're like, Dr. Warren, you're forgetting something. All over g of x squared. And this holds for all x. This holds for all x. So this is the derivative. It's just your quotient rule. It's just your quotient rule flashcard that we have. But in this case, f prime is equal to k times f of x. So this is k times f of x times g of x. But g prime is also equal to k times itself, g of x. And this is over g of x squared. And this is for all x. But if you look here, we've got a k f of x g of x. We've got an f of x k g of x. Commutative property lets me move this k where I want. You can just look. These three products are the same. So these guys are going to cancel each other out. And we're going to get that this is equal to 0 over g of x squared. But this is going to then be just 0, assuming that we don't have g of x allowed to be 0. And so what we have here is a function whose derivative is always 0. We have a function whose derivative is always 0. Now remember that major theorem that we had, where we said, okay, a function whose derivative is always a function whose derivative is always positive, okay, it would be increasing. A function whose derivative is always negative would be decreasing on its domain. And a function whose derivative is always 0, we haven't used yet, would always be a constant on its domain. So then, since this function, f over g's derivative is always 0, then f of x over g of x is always equal to some constant that we'll call c. It's not the same constant as k up there. It's some other constant c. Now this is for all x. The third piece of information we haven't used yet is that f of 0 is equal to g of 0. Well, 0 is included in the all x. So that would mean this constant c is equal to f of 0 over g of 0. Since this has to hold for all x, it holds for 0, but f of 0 over g of 0 is 1. So that means then that f of x over g of x is always equal to 1, which means that f of x is always equal to g of x. So if you can find a function whose derivative is equal to a constant times itself, another function whose derivative is equal to the same constant times itself, and they're both equal at 0, then we know the two functions have to be the same. Okay, and that's going to be foundational in proving the most important property of exponential functions, the most important algebraic property of exponential functions. Okay, so the result from this was that f of x, in this case, f of x has got to be equal to g of x. Now I'm going to let my f of x here be the function e to the x plus 5. And I'm going to let my g of x be equal to e of 5, that constant, times e to the x. Okay, that's what I'm going to let this be. I'm going to let this function be e to the x plus 5, and this function g of x be e to the 5 times e to the x. Okay, so now let's take the derivative. Let's take the derivative of f. Okay, now I'm going to use this flashcard here because this is not just x. the derivative of e to the x plus 5, so this guy is now in the f of x location, is going to be e to the x plus 5, okay, and then times the derivative of x plus 5. Okay, so all I'm doing is using this flashcard. Well, this would be equal to e to the x plus 5 times the derivative of x plus 5, but that's just 1. So this would be equal to e to the x plus 5. Okay, well, let's take the derivative of g prime of x. Well, this would be the derivative of, using power rule, using product rule, the derivative of e to the 5 times e to the x plus e to the 5 times the derivative of e to the x. But e to the 5 is just a constant, so that's equal to 0 times e to the x. And the derivative of e to the x is this flashcard is just e to the x. So that's plus, my brain's going faster than my hands, that's e to the 5 times the derivative of e to the x, which is e to the x. Or this is equal to e to the 5 times e to the x. Now notice in both of these cases, f prime is equal to e to the x plus 5, but f is e to the x plus 5. So this is equal to f. G is equal to e to the 5 times e to the x. So that's equal to g. Okay, so let's look at this again. F prime of x, we walked through, was f of x. So we've got that f prime of x is equal to f of x. And g prime of x is equal to g of x. So this is exactly this scenario where the constant's just 1, Notice the constant's just 1. Now let's look at f of 0. So let's plug a 0 in. F of 0 would be equal to, wherever I see an x, I'm going to put a 0, would be e to the 0 plus 5, which is just e to the 5. And g of 0, let's put a 0 in. Wherever I see an x, I'm going to put a 5, is equal to e to the 5 times e to the 0. But remember last time, we had that e to the 0 was 1. That was one of our results from last time. E to the 0 is 1. So this is equal to e to the 5 times 1, which is equal to e to the 5. So f of 0 is e to the 5. G of 0 is equal to e to the 5. And they both match this. Well, the only what we showed then was that f of x has got to be the same thing as g of x. In this case, f of x has got to be equal to the same thing as g of x, which would mean then that e to the x plus 5 is equal to e to the 5 times e to the x. Now I'm just going to switch this around using commutativity. Or e to the x plus 5 is equal to e to the x times e to the 5. Now the 5 wasn't important. It was just a constant. If I changed it to a 7, nothing would have changed. If I made it a 21, nothing would have changed. In fact, for any real number, e to the x, let's just call the other real number a, we can argue is equal to e to the x times e to the a. And this is our first major property. of the algebraic major property of the exponential function. And most of the time, we write it like this. That e to the a plus b, because x could be any real number, a could be any real number, b could be any real number, is equal to e to the a times e to the b. Okay, but we just saw why that's true. That e to the a plus b is equal to e to the a times e to the b. And this is a really, really important result for exponential functions. Now let me show you how this result gives us more results. I know you're already bored. I know you're already. You guys don't understand what a magic piece of mathematics that is there. Just how beautiful that is. Now let's use this. E to the any real number plus any real number is equal to e to that real number times e to the other real number. And we also know that e to the 0 is 1. Okay, so now let's use this. Let's box this. And let's box this. Let's make them flashcards. Okay, we'll have this one be our third flashcard. E to the 0 equals what? And 1's going to go on the back. 4 is e to the a plus b is equal to what? And e to the a times e to the b is going to be on the back. Okay, so these are our third and fourth flashcards for our exponential functions. Now, 1 is equal to e to the 0. We've got that. That was from last time, by the way. We defined our exponential function. But this is equal to e to the a plus negative a for any real number a. Okay? A's got an additive inverse. A plus negative a is 0. But then using this property that we just derived, we've got e to the a plus b. My b is now negative a. Then this is equal to e to the a times e to the minus a. Okay, well, looking here, this would imply just matching sides here. 1 is equal to e to the a times e to the minus a. Now divide both sides by e to the a, and you get 1 over e to the a is equal to e to the minus a. And so this shows us that if you've got, like, for example, e to the minus 2, that's the same thing as 1 over e to the 2. E to the minus 5 is the same thing as 1 over e to the 5. So e to the minus a, and I'm not going to make this a flashcard because it's going to be included in something else, but I will write it over here and put it in a box. So we now have that. Now let's look at e to the b minus a. Let's look at e to the b minus a. Well, this is equal to e to the b plus minus a by the definition of subtraction. But using this rule now, where my a is kind of like my b, seriously, Dr. Warren, and my b is kind of like my negative a, then this is equal to e to the b times e to the minus a, just using our flashcard that we derived right there. But we just showed over here e to the minus a is the same thing as 1 over e to the a. So this is e to the b times 1 over e to the a, which is equal to e to the b over e to the a, which is equal to e to the b over e to the a. And we're going to make that a flashcard. So that's going to be our fifth flashcard, which is e to the b minus a is equal to e to the b. Oh, I want to put this as a front of the flashcard. In my back of the flashcards, it's equal to e to the b divided by e to the a. Is equal to e to the b divided by e to the a. So now you've got 5 flashcards. You've got 5 flashcards. Okay, stretch, stretch, stretch. There's one other major algebraic flashcard. There's one other major algebraic flashcard, okay, that we need to get, and that's this one. Suppose I've got this function f of x, that's e of x raised to the 7th. Okay, I've got f of x, that's e of x raised to the 7th, and I'm going to have this other function g of x, which is going to be equal to e of 7 times x. Okay, so I want you guys to look at those. Those are 2 functions. One is e to the x raised to the 7th, and the other one's e raised to the 7 times x. Now I want you to notice f prime of x, here we got to use power rule. Here we got to use power rule. Remember this flashcard. The derivative of anything raised to the k is k times f of x to the k minus 1 times f prime of x. So if I'm looking here, this is like my k, that's my 7. So using that, this would be 7 e to the x to the 6th times the derivative of e to the x. But the derivative of e to the x is just e to the x. Or we get that this is 7, just using we've got an e to the x to the 6th times another e to the x. This is like an apple to the 6th times an apple, which would just be an apple to the 7th. This is e to the x raised to the 7th. But you're like, Dr. Warren, f of x is e to the x to the 7th. Yeah, so this is 7 times f of x. This is 7 times f of x. Okay, so what we've shown is that we've got this function where f prime of x is 7 times f of x. Now let's come over here and look at this function. Let's take the derivative of this. This one's a little bit easier. We can just use our second flashcard. The derivative of e to the f of x is e to the f of x times f prime of x. So this is just e, write it down, e to the 7x times the derivative of 7x, which is e to the 7x times 7, which is equal to 7 times e to the 7x. Now this is sweet. G of x is e to the 7x. So this is 7 times g of x. So this is a function whose derivative is, this one's a function whose derivative is 7 times f of x. Notice that the k is 7. This is a function whose derivative is 7 times g of x. Notice the k is 7. Now let's look at f of 0. F of 0 is e to the 0 to the 7th, which is 1 to the 7th, which is 1. Here, g of 0 is e to the 7 times 0, which is e to the 0, which is 1. So f of 0 equals g of 0, which equals 1. And once again, we're in this scenario, which would then mean that these two functions, f and g, have to be the same. Have to be the same. And this is sweet. This shows you that e, and guess I'm running out of space here. This shows you that, I guess I just erased what I wanted. So I just erased literally what I wanted. Remember g of x, let me write this down, was e to the 7 times x. This shows us that e to the x raised to the 7th is e to the 7 times x. Now again, the 7's not important. The 7's not important. It could be any real number. E to the x to the p is equal to e to the p times x. And these are properties of the exponential function you memorize, but you never actually were shown why it's true. You were never actually shown why it's true. And so I guess my last algebraic flashcard, for this will be number 6, which is that e to the a raised to the p is e to the p times a, is e to the p times a. Okay, and we justify this essentially using quotient rule. How sweet is that? How sweet is that? Okay, so these are 6 flashcards, and I guess I'm a moron. I should have put, this is my front. That's the back. That's the back. Okay, okay. Woo! That's, I know, I'm excited, you're not. But these are properties from high school, guys, that you never quite knew why they were true. You just memorized them. But today, for the first time, you actually see why they're true. Okay, this is the last important property that we really need to nail down before looking at problems, okay? Like the ones that I've assigned, I want to look at e to the x. Like, okay, Dr. Martin, who cares? Well, this is equal to e to the 1/2 x plus a half an x, because a half an apple plus a half apple is a whole apple, right? So e to the x is equal to e to the 1/2 x plus e to the 1/2 x. But then using this, where a is the 1/2 x and b is 1/2 x, then this is equal to e to the 1/2 x times e to the 1/2 x. E to the a times e to the b. But this is equal to e to the 1/2 x squared. But we know that any number that's squared is greater than or equal to 0. Now we can argue, and I'm not going to do this here, that if e to any number is 0, then e to all numbers are 0. And we don't, no, sorry, yes, e to all numbers are 0. And we know that e to the 0 is equal to 1, and that we can't have. That we can't have. There's not going to be any real number where e raised to it is equal to 0. And if you really want to know why, just ask me, and I can show you why. I mean, I guess maybe I can explain it a little bit, because then e to the 5 would be equal to e to the 5 plus a, e to the 5 minus a plus a, but this would be equal to e to the 5 minus a times e to the a. But if e to the a is 0, we get e to the 5 minus a times 0, which is 0. And 5 was unimportant, so all the numbers would be, I'm a mess, I'm dropping stuff everywhere. So everybody would be 0. So we get that e to the x is always positive. E to the x is always positive. With this result, my exponential function is always positive. Now this is fun because the derivative, if f of x is e to the x, then the derivative of e to the x is e to the x, which means its derivative is always positive. Its derivative is always positive. And what do we know about functions whose derivative is always positive? You're like, well, Dr. Warren, that means they're increasing. Now let's look at the second derivative. The second derivative would be another derivative of e to the x. Since the first derivative is e to the x, the second derivative would be e to the x, which is also positive. But if the second derivative is positive, that tells you the function's concave up. That tells you the function's concave up, which means it's always smiling. So we have a function that's always going up, it's always smiling, and at 0 it's 1. So its graph has to look like this. At 0 it's 1, it's always going up, and it's always smiling. So it can never touch the x-axis. It keeps going up, and it keeps on smiling all the way up. And so the graph of my exponential function looks something like this. The graph of my exponential function looks something like this. Okay, now we're going to use the fact that e raised to anything. My 7th flashcard is e raised to the apple is always greater than what? And on the back, I want you to put 0. E raised to literally anything is always 0. Now you say that. E raised to literally anything is always 0. E raised to literally anything is always 0. E raised to anything is literally always 0. I guess that wasn't a very good rap. Okay, you try it. E raised to literally anything is always 0. Now I'm going to show you this helps in working problems where you're working with e to the x. These results are so much fun, guys. I know you're not a geek like me, but these results are so much fun. Okay. So now I've got some questions from the book that are much like the questions that I asked. In fact, I assigned the odds. Here's a couple of the evens. I forget which one this one is, what number it is. But here was a question that asked for, what's the tangent line? What's the tangent line to the function f of x equals e to the minus x squared when at the point 1e? Now let's just first of all make sure they've got this right. Is when x is 1, f of 1 is e to the minus 1 squared, but 1 times 1 is 1. And by that property we just had, e to the minus a is 1 over e to the a. So we get 1 over e. So we don't have it right. It's 1 over e. It's 1 over e. Okay, well that's good. I'm glad I checked it. Okay, so we're looking for the tangent line to the function f of x equals e to the minus x squared. Okay, at the point 1 over e. Now when I say tangent line, ding, you write down what? When I say tangent line, just like Pavlov, you write down what? I hope you're like Dr. Warren, y minus f of c equals f prime of c times x minus c. Give me a cookie, Dr. Warren, give me a cookie. Ding! Now who's your c? And hopefully you're like, Dr. Warren, that's the 1. Who's the f of c? Well, this is this guy, so this is my c, this is my f of c. So let's just use that. We'd have y minus f of c, which would be, I'll even put the 1 in here so we can do this in 2 steps. Wherever I see a c, I'm going to put a 1. Okay, but I know my f of 1 is 1 over e. It's just a number. It's just a number. Don't let it bother you. You're like, hey, Dr. Warren, are we done? No, we're not done. We still have to find the f prime of 1. So now, let's take the derivative of this function. So how would we take the derivative of that? It's e to the f of x, so let's do this. What's the derivative of e to the f of x? And like, Dr. Warren, it's too hard. It's too hard. No, it's too easy. That's the problem. It's too easy. You just take this thing and you write it down again. Then you take the derivative of the exponent. That's what the rule ended up being. Now let's look at this. This would be e to the minus x squared times the derivative of minus x squared, which is minus 2x, which is minus 2x. Now we wanted f prime not of x, but we wanted f prime of 1. So wherever I see an x, I'm going to put a 1. Which ends up being, if we just clean this up a little bit, e to the minus 1 times minus 2, which is like minus 2 over e. I don't care, you could use this. But I'll write it like this. So then the equation of my tangent line is this minus this number times x minus 1. So there's the equation of the tangent line. Now, I swear, if you show your parents this stuff, they'll think you're geniuses. They'll think you're geniuses. If you show them this, they'll think you're geniuses. But you don't have to tell them, all I did was really just write that thing down again. That's all I did was just write that down. And then I took the derivative of that thing. You don't have to tell them that. They'll just see all this exponential notation and they'll think like, wow, my students are really getting their money's worth. Okay? But you're like, Dr. Warren, I'm with you every day. I know we're not getting our money's worth. I know we're not getting our money's worth. Now here's the next problem. I know my 15 minutes are getting close, so I've got 2 more exercises that I'd like to do. I may be a little over today. I apologize. I'll try to cut time next week. Here's a function where they ask, when is this function increasing and decreasing? And you're like, you're out of your flipping mind. That's an e to the minus x. There's no way I can plot this thing. There's no way I can find out when this function's increasing and decreasing. And I'm like, just remember, e to the anything is always positive. So how do we find intervals of increase and decrease? And you're like, oh, I don't remember. Guys, you're going to have a test. You're going to have a test, okay? So how do you find intervals of increase and decrease? You're like, oh yeah, a sign chart for the first derivative. So let's take the derivative of this. Dr. Warren, I can't do it. You can do it. Let's use power rule. It'd be the derivative of x squared. I can do that, Dr. Warren. Times e to the minus x. Remember the big plus. How disappointed we were when we found out that was in the product rule. The first times the derivative of the second. I'll never be able to do that. Yes, you will. Can you do this? And you're like, yes, I know that derivative is 2x. Okay. Now, this one, the x squared, you're not even thinking. This is an e to the f of x. It's minus x. So we've got to use that flashcard. It's just e to the f of x times the derivative of minus x. Oh, Dr. Warren, that's not so bad. What's the derivative of minus x? Well, that's just 1. Times minus 1, or that, just cleaning up a little bit. I'll just make that minus 1 into a minus there. And you're like, well, what do we do now, Dr. Warren? Well, what did we do with the other problems? What did we do when we took the derivative with the other problems and we're trying to find intervals of increase and decrease? We factored. Well, I can't factor this. Well, what's alike in both of these? What's alike in both of these? And you're like, well, this dude's the same. This guy has 2 x's. This guy has 1x. So let's pull out this guy, e to the minus x, and let's pull out one of those x's. And let's see what we got left inside the parentheses. Well, the only thing left in here that's missing is this 2. We've got our minus sign there. We've taken that guy away, and we've taken one of the x's. So we're left with this. Okay, now let's create our sign chart. Algebraically, when will my derivative be equal to 0? I don't know, Dr. Warren. Well, what would make this term 0? What would make that term 0? And you're like, okay, that one's not so bad. 2 makes that guy 0. Well, what would make this guy 0? Well, Dr. Warren, that's an x. The only thing that would make that 0 is 0 itself. And that's 0. Well, what would make this guy 0? Nothing. Nothing will make that 0. E to the anything is always positive. So these are the only critical points. X equals 0 and x equals 2 are your critical points. So now all I have to do is test. Now remember, these are the only zeros, so give me a number bigger than 2. And you're like, 3. Okay, let's try 3. And again, e to the minus 3, e to the anything, positive. 3, positive. 2 minus 3, negative. So I got a positive times a negative, and I'll get a negative. Now I'll let you guys play around and get that fact that this will be positive in here, and this will be negative in there. Okay? Which means I'm decreasing, I'm increasing, and I'm decreasing. And so if they were asking for intervals of increase, it would be between 0 and 2. And for intervals of decrease, it would be between minus infinity to 0. And then we get our welder out, pulling this together, to infinity, from 2 to infinity. Okay, so even though you've got this e to the stuff, it's not hard. It's not hard. If you remember your flashcards. Okay, now we're going to look at one last exercise, one last one, okay? And this one's going to be a little bit more involved. And then I'll call it a lecture. But I want to make sure I give you 3 decent examples in trying to attack these problems. In this last one, they give us this function. You're like, yuck. X times e to the minus x squared on 0 to 2. And they're asking us to find the global max and global min. You're like, ugh. There's infinitely many points between 0 and 2, but remember the theorem that says global maxes must occur at an endpoint, or a local max. Global mins must occur at an endpoint or a global min. If we got a function that's continuous on a closed interval, then that's the rules. So let's go try to find local maxes and local mins. I'll take the derivative. Again, I'm a little bit scared, but I'm not going to worry about it. Product rule, it's going to be the derivative of x, derivative of the first times the second, plus the first, times the derivative of the second. And you're like, Dr. Warren, I'll never be able to take the derivative of that. You will. The derivative of this is 1. So we're just left with e to the minus x squared here. The derivative of this one, we need that e to the f of x flashcard. If you don't think, you just write it down again. Just write that down, then times the derivative of that exponent. The derivative of e to the f of x is e to the f of x times f prime of x. Okay, so now we're there. There's our derivative. There's no more taking any more derivatives. We're done with that. Let's factor. What's alike in each of these terms? Well, in this case, it's just the e to the minus x squared. Now, what I'll have left here is just a 1. What I'll have left here is this guy times that guy. X times minus 2x, which is minus 2x squared, which is minus 2x squared. Now this one's a little bit harder to factor. We're trying to find when the derivative is 0, but e to the anything is always positive. So this can't be 0. So the only way my derivative is going to be 0 is if this guy is 0. If this guy is 0, which is the same thing as saying 1's got to be equal to 2x squared, or x squared's got to be equal to 1/2. Now, all I've done is set this equal to 0, divided by 2. Now this is where we go a little bit irrational, a little bit crazy. This is equal to plus or minus the square root of 1/2. This is equal to plus or minus the square root of 1/2. Now remember, our domain is between 0 and 2. So that's all we're concerned about. So let's create a sign chart. Well, let's start creating a sign chart. Now whenever I'm doing global maxes and global mins, I want to put the domain in here. So these are endpoints. These are endpoints. Now notice only one of my critical points is actually in here. So let's put the square root of 1/2 here. This makes the derivative 0. And this makes the derivative 0. But this guy is not in the domain we're interested in, so we can actually ignore him. Unlike if we're looking for intervals of increase and decrease, we can't ignore him. Okay? Or if they were asking us local maxes and local mins and not on the closed interval 0 to 2, we couldn't ignore him. But because they stuck us specifically in the 0 to 2, we can ignore this dude. Okay, so now what I have to do is try to figure out what's going on with this sign and what's going on with that sign. So might be nice to know what the value of the square root of 1/2 is. Okay, and so let me see if I actually wrote that down. I think it was like maybe 0.707, something like that. 0.707. Because I needed some other number up here, but since it's just 0.707 and then a lot more decimals follow, like an infinite number. Okay, I can test with 1. Okay, so let's put a 1 into the derivative. So I come back down here, e to the anything's positive, then I got 1 minus 2 times 1 squared. 1 minus 2 times 1 squared. Well, 1 squared is 1, times 2 is 2, 1 minus 2, negative. So I know I'm negative in here. We could test by putting in a number in between here and here. Something like 1/2 would be less than this. E to the anything's positive, when I put a 1/2 in, 1/2 squared is 1/4. Let me get that out of the way. I put a 1/2 in, 1/2 squared is 1/4. 2 times 1/4 is 1/2. 1 minus 1/2 is negative. So 1 minus 1/2 is positive. So I'm positive everywhere here, or else I'd have another 0. So we know it goes like this. Okay, so we know it. But that means that the function's increasing and then decreasing on the intervals I'm interested in. So that would make f of the square root of 1/2 a local max. And so if I'm looking for my global max, I've also got to include these two guys, my 2 endpoints. Okay, so I got to figure out the numerical values. Of all these. Put them in the octagon. The biggest one's the global max. The smallest one is the global min. Notice, since we're going up and then we're going down, this guy's got to be the global max. One more time, Dr. One, what'd you say? Since we're going up and then we're going down, this guy's got to be the global max. But we'll find numerical values for them. If I look at f of 0, now remember, you put it back into the original function, not into the derivative. Back into the original function. This is the thing that we're looking for maximums and minimums of. F of 0 would be 0, because we're going to get 0 times e to the 0, which is 1. 0 times 1 is 0. E to the 2 is 2. E to the minus 4, because 2 squared is 4. Then f of the square root of 1/2, well, that's a little bit nastier, is going to be the square root of 1/2 times e to the minus the square root of 1/2 squared, which is like square root of 1/2 times e to the minus 1/2. And when you get numerical values for this, this is like 0.03, a bunch of numbers after. No, this is 0.0. This guy's right here, 0.03 with a bunch of values right after. And this is 0.09 with a bunch of values right after. So we can see this guy's in fact is just like what we thought. This is my global max. So this is the champ. And then 0 loses. This is my global min. So this is the way you handle problems like increasing, decreasing, maximums and minimums. When you got a function like that has an e to some power with it. It's not that hard. It's not that hard. The most important thing is this flashcard. And then the other thing is that e to the literally any real number is always positive. Those are the two main things. Okay, I know this was a long lecture. I apologize. But hopefully you learned some things that you didn't know today, and then and also learned some of these other things. All right. I apologize for being too long. Hope you guys have a great weekend.